All right, so we had the wave equation, and it describes the displacement of the particles. So we accomplished, back up here, we accomplished finding all about this guy here. But we want to get to energy, and energy propagates with the speed of the wave, not the strictly the displacement. And so we're going to now go through one more derivation of the wave speed, nu, which is present in our wave equation, and we've been utilizing it throughout, but we're going to come up with an expression for it here. Then, after that, we get to talk a little bit more qualitatively about a couple more wave topics. So we're going to do wave speed, use that to talk about the energy that's propagating, and then we'll talk about other things. So, consider a small segment of string somewhere with a longer length of string under tension. So if we have some long string here that's undergoing some sort of wave, does not matter what wave, we're not assuming the shape of the wave, doesn't have to be sinusoidal, doesn't have to be a periodic at all. We are going to say this is the x direction here. We are going to consider a tiny little segment, delta x, right here. So that is our segment. So keep in mind that's what we're doing. We're picking out a small section. So let's make some assumptions. Let's say the string is perfectly flexible, so we don't have to deal with any kind of hard, weird stuff. And we'll ignore the force of gravity since there'd be no reason. It's not a real scenario. We're just trying to get out the behavior of the wave, not the wave in real life under normal conditions. So we're isolating just the behavior of the wave. So let's give the string a mass per unit length. So mass per length of mu, which means that if our length is equal to delta x, then our total mass, m, is equal to mu times delta x, the mass per length times the length. All right, so now let me draw out this segment a little bit better here. I think my palms are getting conductive as I go. It's jittering the screen around. All right, so that's x. So we have our small segment like this. It has some curvature. It's not dx, it's delta x. I guess there's a philosophical argument whether there's a difference there, but we're going to consider that it has length enough that it still allows for some sort of curvature, some sort of changing slope. So now, what we're considering is the forces that the segment of string on either side, the rest of the string on either side, the forces that those two sides of the string exert on our segment. So there's a tension force, and that's what it all kind of comes down to, and that's what causes this, this interaction propagating from one segment to the next. If you imagine a rope with zero tension, what you're imagining is a system of dissociated particles. If you were to lift up a string with zero tension, if you were to lift up the beginning of it and put it back down, you've not caused a wave, you've just lifted up a particle and put the particle back down. There has to be some connection, and that's the tension force, and that's what allows the wave to propagate. And so this tension force exerts, let's see if I can do this a little better. It exerts a force on either side here. I'm going to move this guy out of the way, actually. Move him up there. And it is completely in line, let's see if I can do it, completely in line with the slope of the line at that point. So like, I don't know, maybe there. Like that. Call that F2. And this is a point. This is, we'll say x, and this is x plus delta x. Over here, the other part of the string does the same thing and exerts a tension force completely in line, something like that, with the slope at that point, because that's how string works. Tension doesn't exert any kind of odd perpendicular force. It's just along the direction of the string. So it has to be in line with the slope. So now, let's consider the components of each of these forces. So we have an x and a y component, right? And so this guy has component here and here that can be broken up into. And this one has a component here and here, right? Or I'll do it up here. There. And he was F1, of course. All right, so since this is a transverse wave, the motion of the string, the motion of each of the particles on the string, the motion of this segment, is only transverse, meaning the wave in general is propagating that way, but the displacement, again, is only up and down. It's only up and down. So that means that we can declare some things about our components. That means that there can be a net vertical force one way or the other, but there cannot be a net horizontal force, because that would mean that particles are either moving to the right or moving to the left. But transverse waves, mechanical waves, they don't transport mass. They're not actually moving the particles forward or backward in any net displacement. They're just perturbing them from a position and then putting them right back vertically in a transverse wave. So what does that mean? Well, that means that this component, we're going to call it F for the x component, because it kind of represents tension. That must be equal in length to that component. I don't know if it's accurate to the drawing, but this length, if this were a physical system, would be equal to that length. All right. What isn't equal is, of course, this length and that length. So we're going to give these a name. And those are allowed to have a net force, because it can be on its way up or down, right? That's the restoring force. That's where that acceleration comes from moving the particles up or back down, right, that we were looking at in the graph before. So this is going to be Fy1, and this is going to be Fy2. All right, and this F is equal to that F, and we're just calling it F for simplicity. So to find the total, or to find the y components, Fy1 and Fy2, we can draw this really interesting relationship that I sort of hinted at before. These tension forces have a relationship with the slope of the string. They're exactly in line with the slope at the ends of the string, right? And so if slope is rise over run, right? So slope, rise over run, then we have a similar thing with the components of the forces. So if you say that Fy1, I think is how I wrote it, divided by F, you're declaring rise over run there. And so you're defining a slope. And so since we're talking about this guy, Fy1 is negative, and we're going to take this F as just the magnitude of F, because we can say it's this one, which happens to be negative, or that one, which happens to be positive. We just want that quantity. So we'll consider the magnitude, or we'll consider it positive, whichever way you want to think about it. And so that means that, that this quantity must be the negative of the slope, because this slope is positive. And yet, if you do Fy1 divided by F, with F being the positive magnitude, then you would get negative, right? So we have to say that it is equal to the negative of the slope. And we'll write slope the proper way here as the derivative of y with respect to x. And we also kind of have to specify that this is at x, because it would be a different thing if it were at x plus delta x over here. Then we would have a different y component. So we have a separate expression for Fy2 over F is equal to this one. You don't have to have the negative there, because Fy2 is positive divided by a positive F. That's positive, and the slope is positive at that point. So you can just write down the slope. And that is at x equals, x equals x plus delta x. All right. So remember, the reason that we were able to relate the components of the force to the slope, which is kind of a bizarre relation, is because that's how tension forces work. They just go along the direction of the string. And so if we're considering this short segment, which has some small curvature, at either end, you can relate the components of the force, which are pulling directly in line with the rope, to the slope at that point. And so you get this relationship between the shape of the rope and the forces that are going along. All right, so now we can find the total y component of the force by adding them together to find the net y. I'm going to switch back to white here so it doesn't get too blood intense. Fy is equal to Fy1 plus Fy2. And that is equal to F, so this guy's going to move over, right? F times dy dx at x, or we'll do this way, x plus delta x minus dy dx at x. All right, you follow that? Okay, so here's the next step. So now we have an expression for net force in the y, right? My hand almost wants to just continue this expression, right? So net force is equal to Newton's second law, ma, right? So we have m that we wrote down earlier. This total mass is equal to mu times delta x, and we just found an expression for the total y force. So let's finish it out, and we can solve for the acceleration. So if we rewrite the above, but sticking in mass, we have the total y component of the force, the net force, dy dx at x plus delta x minus dy dx at x is equal to ma, and our m is mu times delta x, and our a would be d squared y over dt squared. This is acceleration of the particles. It's not a derivative with respect to x. We're not talking about the curvature of the string. We're talking about the acceleration of the particles, a derivative with respect to time. All right. So now, if we rearrange this expression into another form, I'm going to bring this f over here, and I'm going to bring the delta x over there. Then we get dy dx at x plus delta x minus dy dx at x, all that divided by delta x, is equal to mu over f acceleration, d squared y over dt squared. Okay, so now we remind ourselves of calculus, and we take the limit of all this as x goes to 0. Right? So we take the limit as x goes to 0, then delta x becomes another derivative, and so the left side becomes the second partial derivative of y with respect to x. So then you get d squared y dx squared is equal to mu over f d squared y dt squared. Holy cow, what does that look like to you guys? Does that look like something familiar? Right? We have a second partial derivative with respect to x and of y, right, of the wave function. And we have on the right side a second partial derivative with respect to t of the wave function. And we have some other constant in here. Oops. We have some other constant in here doing its thing. Wow. So that means that this quantity mu over f must be equal to 1 over mu squared. Which means that our wave speed, in terms of the mass per unit length of the string and the force, the tension force, is equal to f over mu. And so, if you remember, we didn't make any assumptions about the shape of the wave in our derivation. So this wave speed, as well as, like we said, the wave equation, is valid for all waves on a string, all waves that have any shape. And it turns out that mechanical waves of many kinds, not just stretched string, have this same general form for the wave speed. So this wave speed right here isn't applying to all waves ever like the wave equation, but in general, the wave speed of any mechanical wave has that same form of having a restoring force up top and an inertia term down below. And so that same general form is found for all kinds of mechanical waves. So next we talk about energy. We're going to use a very similar argument, looking at a segment again, to see how the energy propagates from one segment to the next. And then we'll talk about some qualitative topics.